make some survey of, its current status. So what is the problem? It's called the tree augmentation problem, or abbreviated by TAP. And it admits a very short formulation of 2 lines. We are given a tree and a additional set of edges, which we call links, disjoint to the edges of the tree. And we want to find a minimum subset of edges such that adding this subset of edges to the tree results in a 2-edge connected graph. So this, for example, in this instance, this is a feasible solution. Yeah, so if we add to the tree the blue edges, the blue links, then this is a 2-edge connected graph, and this is the problem. So it admits several equivalent formulations. One is covering 3 edges by path. So any link defined a unique path in the tree, and we want to find a minimum subset of the path such that that covers all the edges of the tree. So for example here, if this is our solution, we, for every link, draw its path, and the union of the paths should give the entire edge set of edges of the tree. Another well-known equivalent formulation is the problem of covering a laminar set family. So here we are given a graph and with node set V and the laminar set family L on V. And again, we want to find a minimum subset of edges that covers this laminar family. So how is it related? For example, this is our solution. What laminar family it covers? So we root the tree at some node R. For every node, we look at the subtree rooted at this node, and every such subtree defines a set of our set of nodes in the laminar family. And what we should check is that for every such set, there is a link in our solution that has one end in the set and the other end outside the set. So this is the second formulation. So the question, why is it interesting? Why this particular problem is interesting? So the version that I defined is as good as any other problem we consider here, but particularly interesting is the weighted version of the problem, where the links have weights, and we want to find a mean weight solution. So now let's see. So this problem, the weighted version, admits several 2 approximation algorithms. So it can be reduced to finding a minimum weight arborescence. The primal dual algorithm also has performance ratio 2. The iterative rounding method also gives 2, and so on. Now, the weighted up is actually the simplest network design problem for which ratio better than 2 is not known, but is suspected to exist. Well, when I say suspected to exist, I suspect. Some people share this opinion. Others may not, but anyway, there is some evidence that something happens there. And another thing is that the analysis of classic methods for network design problems, the primal dual method, the iterative rounding method, and so on, rely on the analysis how integral or fractional solutions cover a laminar family. So we just say, let's just try to cover a laminar family and see what ratio can we get. And hence, in some sense, it's a threshold problem. Improving ratio 2 for the weighted tree augmentation problem may lead to progress for other problems. For example, Steiner-Forest problems, and so on. OK. So the open problem I want kind of to pose here is achieving approximation ratio better than 2 for weighted up. Now, let's see what was. So one of the ways of achieving approximation, one may consider that maybe what happens if we just take the standard cut LP when we want to and I write it just the unweighted version. Can we, say, design some LP-based approximation algorithm for the unweighted version that achieves ratio better than 2? So this is the natural LP relaxation for the problem, which I'll call the cut LP. So best known ratio for weighted tap is 2. Best known ratio for tap is 1.5. And occasionally, the cut LP has integrality gap at least 1.5. So you might think that these 1.5 and the other 1.5 are somehow related. But this is actually not true, because all better than 2 approximations for tap are not based on the cut LP, and in fact are not related to the cut LP. And in some sense, I'll somehow try to convince you that it is, these algorithms are based on a stronger LP relaxation. So while the main open problem is to achieve approximation ratio better than 2 for weighted tap, we can replace it by more modest open problems. For example, more modest intermediate problems. What is the integrality gap of the cut LP? And let's say even for the unweighted case. Okay, what is the integrality gap? What we know is that it is somewhere between 1.5 and 2. So maybe binary search will solve the problem in the range 1.5 and 2, but this is what we know. Other intermediate problem, can we obtain some LP relaxation with integrality gap better than 2? So can we use some LP, design any LP-based algorithm? Of course, it's desirable to use the standard cut LP. So the technique I think that might handle this is the dual fitting algorithms. So what is the dual fitting approximation algorithm? It produces a solution I to the problem, and usually an infeasible dual solution, such that the value of the solution we compute is at most the value of the dual solution we get. So the dual solution fully pays for the primal solution, and the dual constraints are violated by a factor at most rho, which means that the value of the produced dual solution is at most rho times the optimal LP value. And once we design such an algorithm, we can conclude that the approximation ratio is rho, since the value of the solution we compute is at most the value of the dual solution. This is by property 1, and which in turn is at most rho times the optimal LP value. This is by property 2, and of course the optimal LP value is at most the optimal value. This is how we get approximation ratio rho. Well, not all dual fitting algorithms fit this paradigm. For example, there is a recent paper by Cox, Davis, and Williamson, and they give a 3/2 approximation algorithm for covering monotone set families. But still, this is seems to be one of the techniques that can give approximation ratios better than 2, while contrary to some other methods. Okay, so let me briefly describe how current algorithms that achieve ratio better than 2 work. So all these algorithms, this or other way, are based on the concept of shadow minimal solutions. So let us say that a link U prime V prime is a shadow of a link UV if the path of U prime V prime is contained in the path of V. So every link defines a path in a tree. So one link is a shadow of the other if it covers less, if it covers a subset of the edges of the tree. And an obvious reduction is that we may assume that the link set is closed under shadows. We can just add shadows of all existing links, and it does not change the size of the optimal solution. If we include some shadow in our solution, we can always replace it by the original link without losing feasibility. And the solution is called shadow minimal if no link can be replaced by a proper shadow while keeping feasibility. So for example, this is a shadow minimal solution here. And here's another example. Suppose we start for one solution, and we can repeatedly replace links by the shadow until we get a shadow minimal solution. So both these are shadow minimal solutions. So what are the properties of these shadows minimal solutions? So it's an easy observation that the solution is not shadow minimal if and only if two links in the solution overlap. Overlap means that their paths share an edge, and one of the paths contains the end node of the other. So for example, these two links overlap because, say, this path could and this path share an edge, and the end node of one path is contained in the other path. So of course, if two links overlap, then we can replace one of the links by its shadow. This is why if two links overlap, the solution is not shadow minimal. It's also easy to see that if two links are incident to the same leaf, then they are overlap, which implies that if F is a shadow minimal solution, then the degree of every leaf with respect to F is exactly 1. And therefore, the set of leaf-to-leaf links in a shadow minimal solution is always a matching. Okay, so this is something about shadow minimality. Okay, I see. So this frame should be 1 centimeter to the left. I guess this, because of different versions of the PowerPoint. Okay, so another important concept is twin links and stems. So what is a stem? A stem is just a node of the tree such that if we take the subtree rooted at S, then this subtree will have two leaves. And if there is a link between these two leaves, then this link is called the twin link. So these are twin links and stem. Let's denote by W the set of twin links. And for given a stem S, let's denote by sigma S the set of links that go from a stem S to a node not in the subtree of S. So links from a stem S to outside the subtree of S. Also, using shadow minimality, it's not hard to see that if X is a characteristic vector of a shadow minimal solution F, and we have some twin link in such a solution, in our shadow minimal solution, then there should be at least one link in our solution incident to the stem. Well, actually, I'm saying at least, but it can be easily seen that exactly one. So this gives us the inequality that X of sigma SE is at least XE. Yeah.
At least 1 point. Those two nodes are leaves.
Yes, those two nodes. Twin link connects two leaves. Yeah. And if we have a twin link in a shadow minimal solution, then there is exactly one link incident to the stem. I write at least one link incident to the stem. That's so this concept of twin links and stems and some lower bound that is derived from this is due to Nagamochi and Ibaraki. And now a bit different concept. Also, please shift this frame a few centimeters to the left. The concept of blocking trees, I will not go. Oh, yeah, sure. Why not? I will not go into the. Actually, it feels better than. Yeah, I will not go into details, but essentially, to see what a blocking tree is, we should take some node A, contract the subtree rooted at A into a single node, find a tree in the resulting instance, find a tree with 3 leaves, something like this, and have some links present. So all the red links should be present. So when we see such a structure, and one more thing, maybe the most important, that there should be no links going out of from this contracted node A, no link should go out of the tree. So this is called a blocking tree. And well, I'll skip the details, but let's use another Greek letter, zeta, and denote by zeta, given a blocking tree, a tree like that, let's denote by zeta t prime the set of links incident to non-leaf nodes of t prime. And also by shadow minimality, if x is a characteristic vector of a shadow minimal solution F, then it's not hard to see that there should be some link incident to an internal node of the blocking tree. So this gives the inequality x of zeta t prime is at least 1. So given all these, we can write an LP, yeah, which includes the non-negativity constraints, the ordinary cut constraints of the cut LP, the stem constraints, which say that if we have a twin link in our solution, then there is a link incident to the stem, and the blocking tree constraints, which say that there should be at least one link incident to an internal node of any blocking tree. So that's nice, and yeah, so it has a lot of new Greek letters. Maybe one of the challenges is to write an LP with more Greek letters than here. And we can write, of course, the dual LP. Well, it looks a bit scary because of this constraint. But yeah, we just have 3 types of variables according to the number of constraints we have. I guess I forgot non-negativity constraints. No, it's okay. Yeah, so in this dual LP, different variables play distinct roles. So let me just mention the role of the Z variables. If we increase some Z variable for a twin link, then what happens, the dual load on E itself, on the twin link itself, will decrease. While on the other hand, the dual load on the stem of this twin link will increase. So we have minus whenever we have a twin link and increase its Z variables, we decrease the dual load on this edge, while at the same time we increase the dual load on the links incident to the stem. So eventually, and actually the same thing happens with the Q variables. When we raise these variables, we increase the dual load on links incident to internal nodes. So I would say that this LP in some sense encodes our ability to decrease the dual load on links incident to leaves, and at the same time we can increase the dual variables, which increases the dual load on internal nodes of the tree, on links incident to internal nodes of the tree. So let me just show you some assignment of duals that obeys the rules of dual fitting. So maybe I've gone too fast. So suppose this is our instance. What we do, we find a maximal matching among links which are among the leaf-to-leaf links. But actually, in fact, we also delete the twin links. So here we have 2 twin links, this one and this one. And we delete them as well. And then we find the maximum matching. So in this case, it's only one link. And we denote by U the set of leaves unmatched by the matching. And we assigned value 1 to each unmatched leaf, and value 0.75 to the leaves matched by our matching. And also we add some correction. We find value Z to each twin link such that its both endpoints are unmatched by the matching. So it's not hard to verify, so with this assignment, that for any link, the dual load on every link is at most 1.75. So the dual constraint requires dual load at most 1 So we violate it by a factor of 1.75. Well, let's verify just, for example, for this link. What is the dual load on this link? So it's here. So the dual value of u is 1. The dual value of v is 1. So it sums up to 2. But we made here a correction which should subtract ZE, so it gives actually dual load 1.5. And dual load of 1.75 is achieved between any unmatched leaf and the matched leaf. Okay, that's... okay, and using this LP and following this line, we can design actually an algorithm. Well, it's not a new algorithm. It's a no, yeah.
So is there some intuition that you set the dual variable to 0.5 rather than 0.75?
Here?
Yeah. Doesn't it, I mean, just, how does that enter the dual objective? I mean, this is
Yeah, in the objective, yeah. That's, sorry, just a second. Okay, so the Z variables do not appear in the objective because the right-hand side is 0. This is what
so, you... So, but then why, I mean, if you, I mean, it seems like you've got some slackness in there. And
yes, there is slackness. 1.75 is definitely not the optimal thing, but I want just to show something less than 2. This is the simplest. But in some sense, 1.75 for this simple algorithm is tight because we might have links between matched leaf and unmatched leaf. For example, this link has load 1.75. Okay. Okay, so what the algorithm does, actually it's an old algorithm. It's the same algorithm in all the papers for which we give different interpretation. It finds some subtree T prime and the cover of this subtree. It adds the computed cover to our partial solution I, contracts the tree into a new node, and for the analysis we also keep track of the dual variables. We update, we raise some dual variables in a way so that we won't violate by much the dual constraints. Yeah, so the update of the dual variables is done such that the duals fully pay for the links added, and dual constraints are violated by some factor smaller than 2, in this case 1.75. So now I'll give a full description of the algorithm and its analysis, but of course not now. Yeah, okay. Okay, so before I finish, let me mention something more classic and which I think should play some role in this field. We can actually add, instead of adding various ad hoc constraints, we can add what is called partition or in this case subpartition constraints. These constraints essentially say that if we consider a laminar family and also take also the complement set of the set in the family, and we take some odd collection of pairwise disjoint sets. For example, if we take 3 sets, so we need at least 2 links to cover these 3 sets. And if we take 5 sets, then we need at least 3 links to cover these sets. Of course, we can also take an even collection of sets, but it won't give us new information. And the constraint is that the x value of the links covering at least 1 set in this subfamily should be at least L prime plus 1 over 2. And we know that if we do this, for example, for the edge cover problem, then we get an integer polyhedra. Okay, this defines an integer polyhedron. So since the problem generalizes the edge cover problem, it seems reasonable that this constraint should help. And they do, because just adding these constraints on leaves, on sets corresponding to leaves and stems, it gives the following LP. Well, we have non-negativity constraints. We have constraints corresponding to subpartitions of size 1. So these subpartition constraints implies the stem constraints. And also, if we apply them on the leaves, we get the so-called leaf edge cover constraints. And this LP also has gap less or equal, less than 2, of course, for TAP. So I have a proof that it's at most 1.75, not via dual fitting, via well, some method which are called primal fitting. And probably, but it's probably less. I think it's 5. I almost finished to prove that it's 5/3. Okay, so this is the state of the art. So let me summarize. So what we know now is that if we add some additional constraints to the cut LP, we can obtain integrality gap better than 2. I think with some adjustment and changing of the definition and with some technical work, probably one can do 1.5. Some, or in fact most of these constraints encode the shadow minimality property. And the question is there a better way to encode the shadow minimality property? So a natural way to do that is just to add the constraint xc plus xf less or equal than 1 for any pair of overlapping links E and F. But it seems that just adding these constraints is not enough to do something. However, there is a recent result of Cherry and Xian Gao. They show that if you take the cut LP, add these constraints, and apply the Laser lift and project method, then you get an SDP with gap 1.5 plus epsilon. So this is another possibility to encode shadow minimality. But essentially, all these results are based on this old algorithm of mine, Guy Kotsas, John Feldman, and Guy Evan, which in turn is based on even an older algorithm of Nagamochi and Ibaraki, and the new idea they had about the lower bound for this problem. So among the two intermediate problems, I kind of sketched a solution to one. Yes, we have LP relaxation with gap better than 2 for TAP. We still don't know what is the integrality gap of the cut LP. It's somewhere between 1.5 and 2. We don't know which is the right number, or maybe none of these. Okay, and so we're, of course, still left with the main open problem of obtaining approximation ratio at the 2 for weighted TAP. We don't know what happens there, so if you want to help, maybe some fresh ideas are needed because the current small progress is made by fairly old algorithms. So it's kind of, okay. Was it?
So when you say fresh ideas are needed, do you have instances for these LPs that show an integrality gap of 2 for the weighted case?
No,
so it's possible these LPs are strong enough to, in the weighted case, to have a performance rate, be the basis for a performance ratio.
This LP can be the basis for performance. I guess the one with the partition seems the most powerful. They might be the basis for, at least for unit weights. There is a proof that it has gap less than 2. But yeah, but it would be nice that if the cut LP has gaps less than 2, because it's a simple LP, it's easier to work with. But
that has the gap 2 for weighted.
No. The cut LP, we don't know the gap. It's somewhere between 1.5 and 2. What?
You have to weight it.
For weighted, it's somewhere between 1.5 and 2. For unweighted and weighted, so there is an example for the unweighted case where the integrality gap is 1.5. I guess it's the first thing to study. I would show this example if I had time. Construction of a lower bound of integrality gap at least 1.5. there is, of course, an upper bound of 2 by all possible algorithms.
You showed in the unweighted case how to approximate augmenting a tree to a tree-edge-connected spanning subgraph with approximation rate better than 2. Can you also do this for forests instead of trees? I mean, we know how to do it for the empty forest and for the tree, but anything in between.
So when you say forest, there should be some connectivity requirement somewhere.
Some edges that are free.
Steiner forest.
No, there are some free edges, but they form a forest, not a tree.
To augment it to 2H connectivity from a forest. No. So actually, when the initial graph is empty, we get the 2H connected sub. I didn't mention it because we get the 2H connected, the mean size 2H connected subgraph problem, and of course it admits a ratio better than 2. I think, yeah, am I right? You have a paper. The ratio is 4/3. The current best ratio is 4/3. There were some errors, but yeah. This is not really a particular case of this problem, but it's of course related. I mean,
Especially you can do the 2 extreme cases.
yes. Because you see, in the 2H connected subgraph problem with the empty graph, you have some good lower bound. Here, you don't have. Yeah, that's correct. One last remark. The previous victims of this problem that studied it a lot, and so I guess we'll have a session outside. So anybody that is interested is welcome to join. Okay. Thanks. So between 2 and 4 is the official time. When?
So at 2 o'clock, I guess Chandra and Zeev will lead a follow-up session of their reviewer. So there'll be questions on element connectivity and augmentation.
No, I do have that. But I don't know how to turn, should I turn anything on, or is that automatically on? Seems like it's good. All right.